Okay, so in this short lesson here, what I'm going to talk about is just sort of defining what a function is and giving an introduction to that, and then a little bit of time on how we can determine if something's a function or not. So I wrote out some of the definitions here. Sometimes you'll hear me say that something's well defined, and that means that the result, or you can think of it as the output, is uniquely determined. And specifically what we mean is like by the other variables, or if we plug things in for the other variables, it uniquely determines what the variable you're interested in is. And so we can say that y is a function of x if y is well defined with regards to x. So in other words, what that means is that if x is a particular number, or if we plug a number in for x, then we get one output for y, so at most one corresponding y value. So every input gives you at most one output. Sometimes there might not be an output, but usually there's something. So just some examples. I'll go over the three kind of typical formats that we see for collections of points. So I'll do a first example. And that's going to be actually just a collection of points. And so if we look at, let's say this thing here, I'm going to call it F. And it's going to be a set. So we use those squiggly brackets for our set notation. And let's just make up some numbers here, 0, 1, let's say 2, 5, 3, 6, and let's do, I don't know, 2, 7 there. So that's gonna be the first one, and then maybe I'll call this other one here G. And so this is gonna be our set of points, and I'll do, let's say 0, 1, 2, 5, 3, 6, and 2, 7. Not 2, 7. I'm going to actually repeat 2, 5 here. And so if we look at these, remember, as a collection of points, usually it's written as x comma y. So I'll just make a little note there. Right, so that means x is 0, y is 1. And then similarly for all of those coordinates in those brackets. So what we actually have here in the first one is that with this 2, 5 and 2, 7 point, what we've got is that x equals 2. It actually gives two different y values. It gives y equals 5 or y equals 7. That's two different outputs for one input, and that's a problem. So that is actually going to say it's not well defined. So actually y is not a function. So this system here, this f is not a function. You may be able to flip everything around and say that x is a function of y, but usually we don't want to do that. Usually we want to think in terms of y. So I might actually even say like y is not a function here to be specific. Now if we look at G, so you might be thinking, well, now I can track whether or not something's a function in this format by just seeing if the x's show up more than once, right? Because we have x equals 2 showing up in those two different points. Now over here, my writing's a little messy, but you can also see we do have a similar thing going on here with x equals 2 and x equals 2 here. But what we have in this case is x equals 2, that actually implies that y is 5, or, well, y is 5 in both of them, right? It's the same point repeated. So it's actually just one output for that input. Specifically, only one output, right? That's really different from here, where we actually had, in the previous one, we have two outputs for x equals 2. So that's a really big problem. We don't want that in our functions. This one's okay. You can repeat points. If we were drawing this on a graph, you would just draw a point right on top of itself. It wouldn't look any different. So this is totally a function. And so here I'll write y is a function. And yeah, so that's how we can determine it if something's written as a list of points like this. I'm going to do a second example. So I'm going to get rid of this definition up here. So I can leave that other example for a second. Actually, you know what? Maybe I will. You guys have the ability to pause and go back, so I'll just get rid of that. Okay, so the next thing that we're going to look at is graphs and how we can tell if a graph is the graph of a function or not. So I'm going to draw this pretty roughly. You can see it's a little tricky for me to draw some straight lines here. Let's make like kind of a weird wave curve. Okay, in general, I'm pretty lazy with graphing in that I won't label the numbers if the numbers are 1, 2, 3, 4, 5. Anything you submit to me, you can be equally lazy. So let's say I have a graph and maybe it's like some kind of weird curve like that. And I'll draw another graph over here. And we'll see a graph that looks like this quite a bit later. That's not a very good scale, but that doesn't matter. Label my X and Y. Doesn't really matter if I draw all these arrows. You should kind of get the idea there. Yeah, so in graphs, there's actually something that we can do called the horizontal line test. And I'll illustrate it with these two examples here. Basically what it states is that if we can draw a horizontal line, it should be straight. I'm going to maybe actually use a line feature here to draw this. So yeah, so obviously I've just lied to you, so I'm going to go back and correct what I said a second ago because I'm actually jumping ahead to a later topic. Is if you'll notice, that's a vertical line that I drew. That's the actual line I want. It's called the vertical line test, not horizontal. Really emphasize that vertical line test because we draw a vertical line. And so what you can see in this first picture here, according to the scale that I drew there, that looks like it's about x equals, I don't know, 0.6. It doesn't have to be perfect. But what I can see there is that that's intersecting the graph at 3 different y values. So x equals 0.6 is actually giving me maybe y equals, I don't know, 1.3. Y equals, let's say 2.9. And maybe y equals, that looks like pretty much right on 4. So that vertical line, if it passes through more than one point, it's going to correspond to more than one y value. And that means that it's not a function. So passes through. More than one point. So that's actually our answer for this one because that vertical line passes through more than one point. It's not a function. And I should make note of this. It's not just an arbitrarily chosen vertical line. It's actually any vertical line. Right, so there's definitely vertical lines I could have drawn here, like this one only passes through one point, or this one only passes through one point. but there is some vertical line, particularly this one that I drew and maybe a couple other near it, that does pass through more than 1 point. So it's not a function. And in this case, the opposite of the test is if all vertical lines pass through at most 1 point, so in other words, if no vertical line passes through more than 1 point, then it is a function. And that's what we have here. All of these vertical lines that I draw, I'll never get it to pass through multiple points. And what that means is that every x corresponds to exactly or at most one y value. So that's what we have for this case here. So yeah, so if you're trying to look at a picture of something and trying to see if it's a function or not, just kind of in your head, or even like you can use your hand as a guide, go through and imagine these vertical lines and see if any of them are going to cross multiple points. And that's going to tell you whether or not it actually is a function. All right. Yeah, there will be a fairly heavy graphing emphasis in this course, so it's certainly worthwhile to talk about those. And then finally, probably the most relevant one is going to be the algebraic one. And get so let's do a couple examples. Again, let's say we're going to have these two equations here. So we actually have an algebraic expression. So the first one is 2x plus 3y is 7. The second one, we're not going to talk too much about graphing things like this. Yeah, there'll be an optional section at the end of the course if you want to look it over. But this does make the graph of a circle. And so yeah, by telling you that, you should probably recognize a circle while vertical lines are going to cross multiple points there. But we can do this algebraically instead. So what you're going to do if you're given an algebraic expression is you're going to actually solve for y. And what we're going to do when we solve for y is then see if it satisfies that well-defined word or definition. The first one is it's all actually linear, addition, multiplication, pretty easy operations. So we're just going to move things around as we know and love. So I'm going to subtract the 2x over to the right side. And then I'll just divide by 3 on both sides. And we get this expression y equals 7 minus 2x over 3. This one's a little bit more complicated because y isn't a square, but we just have to undo that square. Same idea, I'll push the x squared over. Now I'm going to undo the square. I do want you to be really careful when you're undoing a square. So if you think about an equation like this, let's say I have z squared equals 4. I think most people will agree with me that z equals 2 will satisfy that. But there is a second solution, negative 2 also satisfies that, right? If you square a negative, the square just cancels itself. So the actual solution to this is plus or minus 2, or plus or minus the root of 4. So when we solve this, it's not just y is square root 25 minus x squared. It's actually plus or minus the square root of 25 minus x squared. So when you see that square root notation, that is defined in this language of functions. The square root, that symbol, it's a function. It has one output. So if I actually did like square root of 4, it's 2. It's not plus or minus 2. It's just the positive one because we want it to be well defined. So that's why we actually have to put this plus minus here. Now what that plus minus does is it actually tells you it's not well defined. So some x's, for example, let's say x equals 4, will actually give 2 different y's. Right, and so if we actually plug that in, we'd get 25 minus 16 is 9. The root of 9 is 3, so we'd actually get y equals plus or minus 3. Right, that's bad in the language of functions. So that is not a function. Now over here on the left, what we've got is like if I plug in x, doesn't matter what x is, I'm going to follow Bedness. I'm going to multiply by 2. And then I'm going to subtract from 7. And then I'm going to divide that output by 3. It's a very, very well-defined set of rules to figure out what y is. And assuming you're doing Bedness correct, you'll never get a different y for the same x. So this actually is well-defined. And so the one on the left is a function. And so that's kind of the general idea. So algebraically, the symbols that you're going to get showing up that mean that things aren't a function, typically when you solve, it's going to be that plus minus. Yeah, there's not really too many other things that are going to come out from algebraic solutions that don't branch into 2 in a different way than this. Yes, if you get those plus minuses, it's going to be a problem. And they happen when y is squared a lot of times. Or sometimes maybe you'll see absolute values. So there are things to look out for. Yeah, this is how you can determine whether or not something's a function. So I'll wrap this one up. And I'll move on to the next one.